Hi everyone, my name is Z. Kui Liu. Today I'm going to present our work on Zentropy theory and its application to ferroelectric lead titanate. My co-authors are Xunli Shang, Yi Wang, and Jinlian Du from Pennsylvania State University. I want to thank the organizer for inviting us to give the presentation. Zentropy equals to Z plus entropy. And Z stands for sum of states for partition function. And the name was suggested by Josh Roberts from the University of Buffalo during a Zoom seminar I gave at Duke University in June 2022. And here's the link for YouTube of that recording. And we started work on this concept since 2008. This is our first paper published in PIB. And in that paper, we postulate the partition function is equal to the partition function of individual microstates in a system with the free energy here. And then the entropy of the system is equal to consists of two parts. One is the weighted sum of the entropy of individual microstates plus contribution from the configuration entropy among the microstates. Pk here is the probability of each microstate in the system. And we have used this method to predict the magnetic transitions successfully, including the critical points. Here's an example for invar alloy iron 3 platinum. As you can see here in this temperature volume phase diagram, there is the miscibility gap with the critical point on top of it. And we also have three curves here for the volume as a function of temperature and fixed pressures from 0 gigapascal, 3, 5, and 7 gigapascals. At 7 gigapascal, and it reaches the critical point. In this purple area, and the volume is decreasing with temperature increasing. So as you can see here, at the ambient pressure, when temperature increases, the volume first increase, and then increases less, and then start to decrease, and then increase again. So symbols here are from experiments. So it's well reproduced by our model or predicted by our model because we had no fitting parameters. As you can see that the area with the negative thermal expansion, it changes as a function of pressure, and then diverges, become minus infinite at the critical point. Okay, so let's discuss what is entropy theory is really about. It's about a multiscale entropy of a system. So we know that for entropy of a system, and we have this configuration from different microstates, because the system consists of different microstates. However, we also know that each microstate would have its own entropy. So the total entropy of the system will include the configuration ones among different microstates and the entropy of each microstate. So that's our equation about total entropy of the system. Now has two contributions from the individual microstates and the configuration among different microstates, which is represented by the probability of each microstate Pk. And then total free energy, or Helmholtz energy in this case, of the system also consists of two parts. One is the weighted average of each microstate, and plus the configuration among different states. If we continue one step further, we can write our partition function of the system with the free energy of the system. Now we have the free energy of each microstate. So that was different from the Landau theory. We can discuss shortly. And for each microstate, there will be sub-microstate. Okay. And then you can see that you can write the same equation for each microstate with the same formula. So you have the sub-microstates, and with the configuration entropy among the sub-microstate. So now this forms a nested formula. So you can go to all states, all the way from the finest scale we can go and to the very large scale, like people are talking about entropy of a black hole or entropy of a universe. Okay, so now we want to compare our formula as entropy formula with the Landau formula. So let's first look at the Landau theory. So Landau theory postulates that the partition function of a system is related to its Helmholtz energy and MVT ensemble. And then you have this partition function of individual microstate or configurations in the system, and with the total energy of each microstate. And then we can calculate the total Helmholtz energy of the system, which is the weighted sum of the total energy of each microstate, and with the statistical configuration from each microstate. And we get the partition by the probability is the partition function each microstate divided by the partition function of the total system. And then we get the entropy of the system. Now you see that they have the total energy here and the free energy there. However, where in our approach, that we start with the free energy. So we postulate that each microstate we should use the free energy instead of the total energy. Okay. And then we got our total free energy of the system will also be with the free energy of each microstate and with the configuration entropy among the microstates. Of course, then our probability is different and the entropy is different. So the difference is that is this term, right? This term is not here. So why it's not here? Well, we know that these two are equivalent if sk equal to 0. Okay, that's actually what Landau mentioned implicitly, because in his paper, a book, they started with quantum states. So theoretically, the quantum state is only one state, so it doesn't have different states for that quantum state. So that's why sk is equal to 0. However, if you look at the literature, when people apply this Landau theory, they didn't start with quantum state. They started with some other states or intermediate state. For each intermediate microstate, then sk is not equal to 0. So we believe that unless you use quantum state, one should use the entropy theory to talk about the partition function and the free energy and the probability and entropy. Okay. Another question is that even for quantum state at a finite temperature, should it be entropy equal to 0? Well, I think that's another discussion we can have. But in principle, if the microstate one uses for the partition function is not 0 entropy, then one should use the entropy theory equation as our equation here. Okay, now let's go one step further about the entropy theory. We talk about the two portions. One is the individual microstate, another one is the configurational. And because we talk about total entropy, then that should be equal to the thermodynamic entropy we're talking about, which is the integration of the heat capacity over T with the entropy at 0 Kelvin. And usually this one is equal to 0, and based on the third law of thermodynamics. Now you see that we have three kind of terms in this equation now. They actually have very nice connections. So what it means is that in the first one is quantum mechanics. Well, from our application, we can calculate the first term from quantum mechanics. Okay, and then by calculating sk, get fk, then we can evaluate the pk, so we get statistical mechanics. We put them together, we get a thermodynamic contribution. So that means this is our measure. We can measure heat capacity, to integration, we get entropy. So the idea is that by combining these two together, we will be able to compare the predicted entropy with the experimental entropy. So we understand that when we get a high temperature, we get inharmonicity. Okay, so we believe that because we capture the all entropy, and then we can predict the inharmonicity. again without the fitting parameters. Okay. So of course we know that the maximum anharmonicity occurs at the critical point because entropy diverges. Entropy to temperature derivative, which is to give our heat capacity, diverges at the critical point. So we applied it to the case I showed before in my alloy at the iron 3 platinum. We also applied to cerium and iron and nickel and some other compounds. In this presentation, we believe our entropy theory also applicable to ferroelectrics. So in this paper, we present our application of the Zentropy theory to morphotropic phase boundary in ferroelectric. We believe it's applicable to superconductor too. So that's what we're working on. So we can apply this to a very classic ferroelectric material as titanate. And the titanate is a low temperature, is ferroelectric, tetragonal. At high temperature, it becomes cubic, pyroelectric, based on the results from X-ray measurements. But again, we have to realize the X-ray measurements is for the average, right, of the system. Okay, so it's average of the system. Of course, from these measurements, we can calculate the volume. Okay, because the volume decreases, right? Volume decreases as a function of temperature. So that's the negative sum expansion I talk about in INVA alloy. So you see, this is the linear sum expansion. Linear this length is decreasing as a function of temperature in the tetragonal region. And when it becomes cubic, it increases. And we also talk about heat capacity, that's entropy derivative to temperature, and you see that it diverges here. Okay, the heat capacity diverges at its transition temperature, and then goes back as heat capacity measurement. And as I mentioned, the X-ray measures average, right? So for these measurements, we believe at the low temperature, you have the tetragonal structure, you have the polarization when the titanium atom moves away from the center. That's a ferroelectric tetragonal structure. At a high temperature, X-ray shows is cubic. So then we believe that the titanium in the middle, and it's symmetric, there's no polarization, and it's cubic structure. But however, remember that the X-ray measurement is kind of a macrostate, right? Macroscopic measurements. But how about the microscopic? Are these the two pictures correct? Or does it represent the microscopic structure of features? But terminally it doesn't. It does not. So this measurement is by the much finer is XF. It measures the individual local titanium environments. Uses titanium edge in XF. So this is published in 1994 in the literature as PRB. As you can see that use XF measurements. This is the solid line here is the X-ray. Okay, but look at the XF you have here. It's actually still tetragonal. It's C and A. Well, A increases a little bit, but C almost does not decrease. So tetragonal above the transition temperature, local environment. And in addition to the tetragonal, you want to also understand whether it's polarization or not, right? Okay, so this shows one. So this is by X-ray. You see, X-ray measurement shows that the titanium displacement distortion move away from the central point. It's decreasing when temperature goes up by X-ray by neutron diffraction, scattering. So it looks at 763, it becomes a non-polarized. That's why we say it's a pyroelectric. However, for the XF measurements, the titanium displacement retains all the way to very high temperature. Well, you have scattering here, but still, it's there, right? So that means above the transition temperature, it's not cubic from the local environment. It's tetragonal and with polarization. So we did some. So then we look at this problem. We said let's do some AB initial molecular dynamic simulation. AB initial or AMD. So in this simulation, the atom is not the classical molecular dynamics. In this simulation, the forces between atoms are calculated from DFT based first principle calculations. So in this case, 753 Kelvin is 10K below the transition temperature. So the overall shape is tetragonal. Oh, it's a cubic. It's almost a cubic, right? However, of course, we know that if you look at each atom, you see that this is the blue one. The blues are titanium atom. This is projections. So you see 3 atoms on the row here. You see the titanium is not in the center position. It moves up, right? Moves to the side. Okay, so it actually rotates all the time. And this one too, it can resolve them. Some of it is more, some of the switches less, right? Okay. Also, is the distance between the titanium and oxygen, right? It changes too. Okay. So it goes closer and further away, closer and further away. So what happens actually is that if you think about this as the c-axis, so it goes like this, and then it goes like that. Okay, and it goes like this. So the c-axis of the local titanium atom at the lunar cell goes to the z direction, okay? Then it goes to x direction, and goes y direction. So now you see that when this switching direction happens, if this one does not switch, then you create a kind of domain war, right? Between these 2 lunar cells, or between this series, two rows of them, or in that direction. So in all 3 directions, you create domain wars, okay? So that's exactly what happened. So what we do now, we do the analysis of individual titanium atoms, just like in the XF experiments. So then we find that at 753, again, the same temperature, what you see that is that so look at the green is for 1 titanium atom, okay? You see it's like C direction, right? And then jumps to A direction, okay? So then in the C direction is like, in the Z direction is C, then A, C, A, C, A, C, right? So it's a C and it's a change direction. Of course, A could be X, could be the X and Y, right? So it's the same, okay? So now what you see, what happens is that you see it's locally tetragonal, but it switches. Of course, during the switch, you get a cubic structure, right? Because you have to go through the middle and it goes the other direction. Okay? So if you decrease temperature to 623, then you see that it stays longer there now in one direction, right? Stays longer, okay? Stays longer, and it switches less often. So if you get even low temperature, it switches even less frequent, and it stays longer, okay, at that temperature. And you go to above the transition temperature, just like this, very close to this one, okay, very close to this one. So now we can take this data and put it in a plot, okay. So now that's what you see here. So this filled black dots symbols are the X-ray measurements. You see that a tetragonal and become cubic. The blue ones are from XF experiments. So it's C is up there, and A is up here, right? So you see A is moving up a little bit, okay? And C maintained almost the same. Now, in our AIMD simulations, we take the experiment CA value, that basically is the black dots, black symbols. So that means above here, overall, the system is cubic. But internally, for each atom, for each titanium, they are still tetragonal, C and A. So that's for the crystal structure, tetragonal to cubic. Right? The next thing is that, of course, we want to compare, look at the polarization, titanium displacement. You see that again, this is X-ray, this is neutron scattering. And the blue one is the from the XF, and the red one is from AIMD simulations. So you have polarization. Polarization maintains all the way up to the way above the transition temperature. Okay, the reason is because the AIMD is atomic scale, right? We look at each atom. XF is also atomic scale, but X-ray and neutron is collectively for the whole system. So it doesn't. So it's really, this is really the system behavior, the macroscopic, and this is really the microscopic behaves. So of course that means if you want to predict the properties, of system, we have to understand the microscopic one so we can predict it. So that's what the Zentropy theory is applied here. Okay, so let's apply the Zentropy theory for that tightening. At the system scale, we have a ferroelectric or PyroElectric. Below the transition temperature is ferroelectric, above is the PyroElectric. So it consists of different microstates. They are all ferroelectric. Okay. And so there's a configuration entropy among them. So what are the microstates we have? We have the ferroelectric without domain without domain walls. We have 90-degree domain walls, 180-degree domain walls, right? So what it means is that when this tetragonal morphology feature turns to from to the xy direction, it becomes 90-degree, or if you switch direction, become 180-degree. So we need to get the energy, the energies of those different microstates, and then we can calculate the entropy, energy, and the partition function, get the probability of each different configurations, different microstates. And for each microstate, we can calculate the entropy, energy, from DFT-based calculations. Okay. So now this is quantum mechanics. This is the statistical mechanics. This would be our thermodynamic properties, like the measure for experiments. Okay, so in the literature, the domain structures and energies have been studied, published many times. For lead titanate, that we found this very comprehensive study back about 20 years ago. Calculated domain was, this is 180-degree, this is 90-degree domain was. And now you see, of course, without domain, we take that as a reference state, zero energy. And 90-degree domain here, domain was, you have the 35 millijoule per millimeter per meter square. And if 180-degree, then it's 132. This is about 4 times difference to this one. So which means that 90-degree domain was are more frequently observed. 180-degree domain was are less frequent in experiments. And so this is the data we use. So we take this data at 0 Kelvin for the time being, because there's no reporting in the literature about free energy, only have 0 K energy. So we take those 2 data, we put in our Zentropy theory, then we can calculate the probability, right? Probability of each different, three of the configuration. Well, of course, we have to consider the multiplicity for each configuration, each microstate. So after doing that, we got our results here. These are our results. So at 0 Kelvin, at a very low temperature, it's 100% of the ground state, and the 0 for the other 90-degree domain was and 180-degree domain was, and the sum of them. Okay, so now you see that around 100 Kelvin, the ground state, the probability of the ground state without domain was start to decrease, and around 675 Kelvin, it becomes 50%. So that's one of the criteria we use to define the transition temperature. And it's about 90 degree lower than the experiment. But remember that we used 0 Kelvin domain energies. We didn't include the entropy contribution. That's because it's not reported in the literature yet. Okay. And there's no fitting parameters. It's complete from DFT data and with our Zentropy theory. So we are very encouraging. So it looks very, very interesting as a comparison. Well, you can see that, again, as you see that the 90-degree domain wall is dominant. And the 180-degree domain wall is much, much lower probability. It reaches below 10% at a high temperature. At transition temperature is like 5% of domain walls, of 180-degree domain walls, and about 45% of 90-degree domain walls. So that's an agreement with experiments. So we're very encouraging. So what's next we're going to do is that we're going to continue to work on this one, where we're going finish the calculations very soon and publish it. So in this presentation, we discussed that we introduced our Zentropy theory, and we believe Zentropy theory can be used to predict the high temperature properties, and can account for the inharmonicity of any material to the extreme, which is the critical point. And we reconciled the discrepancy between the Landau theory and the Zentropy theory in terms of total energy used in Landau theory and the free energy used in our theory. And we applied the Zentropy theory for the ferroelectric transition in lead titanate with very good agreements so far. In the future, we're going to predict the free energy of the macrostates using our high throughput DFT-TK software, and use our mixed space approach for polar materials. We hope our prediction will be even closer to experiments. The reason we believe that because in our magnetic materials prediction, when we introduced the free energy, the agreement with experiments is with a few degrees, without any fitting parameters. With that, I want to thank you for your attention. Please email us your questions and comments. Thank you very much.